This is the solution video for question 14 from paper 2 of the 2019 TMUA or CTMUA exam. In this question we're asked to consider statements about a polynomial p of x for a less than b. Statement 1 is that p of a is less than p of b. Statement 2 is the derivative of p at a is less than the derivative of p at b. And statement 3 being the second derivative of p at a is less than the second derivative of p at b. We're then asked which of these three is a necessary condition for p of x to be increasing for x between a and b inclusive. And we're given 8 options varying from none of them are necessary to all of them are necessary in varying combinations. So first things first, let's look at condition 1. So condition 1 to be necessary means that if the polynomial p is increasing between a and b, then p of a is less than p of b. Now this has to be true because a is less than b, and p increasing implies p of a is less than p of b simply by the definition of a polynomial being increasing. So we know 1 is necessary because it's a consequence of increasing. What about 2? Well, we know for a polynomial to be increasing, you may have seen that we need the derivative to be greater than 0 everywhere. And this is just comparing two derivatives, so this doesn't feel like we need it for the polynomial itself to be increasing. So we're going to try and construct a counterexample. So we're going to try and construct a polynomial or something that a graph of a polynomial such that p is increasing but p dash of a is less than p dash of b. So let's put a and b down arbitrarily, and we can arbitrarily put p of a and p of b in where this is greater than this. So if we were to construct a counterexample to this, we need p dash a to be small here, p dash of a to be big here and p dash of b to be small here. So the graph needs to look close to flat here, or flat even better, and close to vertical here, or a very large gradient. So a curve like this works, and we know we could construct a quadratic looking like this, because any n-shaped quadratic would look a bit like this. So we know that 2 is not a necessary condition because it's not a consequence of p being increasing, as we have a counterexample. So now 3. Given 2 wasn't a necessary condition, it doesn't feel like 3 should be a necessary condition, and indeed it's not. But how do we build a counterexample to convince ourselves? Well, if we look at b, we need p double dash of b to be smaller than p double dash of a for a counterexample. So this looks like it's at a turning point, which means that the second derivative will be 0. So if we carried it on like that, it would be 0. So if we can make the second derivative greater than 0 or large here, we have a counterexample. How could we do that? Well, if we put a turning point like that and flicked it up, something like this, then we know the second derivative is greater than 0 here. If we extend the graph as so here, we know the second derivative is 0 as this is a turning point, or it's very close to a turning point, it's very close to 0. So this graph violates this because the second derivative at a is bigger than the second derivative at b. How do we know this? We could make a polynomial looking like this. Well, it looks a lot like a cubic. So a cubit, we could make various cubics that would be examples that look like this and would violate condition 3. And so we know condition 3 is not necessary for p to be increasing between a and b. And so we've got 1 is necessary, 2 is not, 3 is not. That matches option B in our answers, and so we know our answer is